So in this video, we're going to look at the method of variation of parameters, and we're going to, of course, look at this for, again, the same type of equations we looked at earlier, which is the second order linear homogeneous, non-homogeneous differential equations with constant coefficients. So once again, we consider this equation that you see here, a d2y dx squared plus b dy dx plus cy, where a, b, and c are constants. We assume that this differential equation, has the following complementary function. Yc is ay1x plus by2x. So we've done that before in the previous video. So how to find the complementary function, which is by equating this equation to 0. So I just labeled that 1 here, which I'd forgotten. So anyway, so this is our complementary function. Now let's see what the method of variation of parameters. Remember, the method of variation of parameters is for finding the particular integral, okay? The particular integral. So let's see. So according to the method of variation of parameters, the particular integral yp, particular integral, is this new function v1x times v1, where you will notice here, I want you to notice that, see here, this is the y1x and this is y2x. So these are what we're putting into here, as you can see. Okay, so they are coming from the complementary function. And these v1 and v2 are new functions, which are defined as, so as you can see here, v1 is minus fx. Fx is the right hand side, you see here, this is fx. Here, there you see, the right hand side times y2, which is again this one. A into the Wronskian, W is known as the Wronskian of y1, y2, and A is the constant that you see here, there you see. And v2 similarly is fx again, see fx, but v2 now has y1, so the opposite, and AW and the Wronskian of y1, y2. So you can see the difference between v1 and v2 is really that when you have v1, you're looking at y2 from the complementary function. When you have v2, you're looking at y1 from the complementary function. The Wronskian is something you would have studied in linear algebra. In case you haven't done linear algebra yet or don't remember it, it's very simple. It is simply the determinant. This is a determinant, as you see here, of so the Wronskian of y1, y2 would be basically y1x, y2x, the two functions. So first of all, Wronskian is for a function, okay, more than one, of course. Here you see y1, y2. So the Wronskian of y1, y2 is then the first row is just the two functions. The second row is the first derivative. Now, if this was y1, y2, y3, you could have the third derivative, second derivative, and so on and so forth. So that's how this is done. It's a square matrix, of course, because you cannot calculate the determinant of a non-square matrix. So in this case, as you can see here, this is how the Wronskian is calculated. All right. So this Wronskian will end up here being the denominator. There you see, this is the Wronskian. Okay. So let's look at an example how we solve this differential, how we find using the method of variation of parameters. So we're not going to go and see how the complementary function is calculated. I'll just do that for you here. There it is. And of course, based on this, the particular integral is set as you can see, yp is v1x times, you see, sine x, and then v2x times cos x. And v1 and v2 are calculated as those integrals, which I've already shown you. These are those integrals. So we'll calculate those now next. So we need the Wronskian first, which in this case is, as you can see, given here. So it will be the Wronskian of sine x cos x. Okay, so that there you see sine x and cos x, and then the derivative of sine x is cos x, derivative of cos x is minus sine x. We calculate that, it's just going to be minus sine squared x minus cos squared x, which is minus 1. Therefore, v1x is equal to minus of tan x, which is the right hand side, the fx that you see here. Okay, it's taken from here, remember. Okay, there it is, tan x. This is the tan x. Okay, cos x is y2 because this is v1, so that goes over here. And the Wronskian on the right hand, this here you can see the coefficient is 1, so that's this one over here, okay, and then the Wronskian goes here, okay, and then we just calculate that integral, and the result turns out, because that's tan x, which is sine x over cos x, it'll cancel the cos x in the denominator, and the result is just minus cos x plus c1. So similarly, V2 is calculated as well, and that turns out to be this here minus log of sec x plus tan x plus sine x. So we've got both V1 and V2, so we've got now our particular integral. So hence we have the following, the particular integral, as you can see. So the V1 multiplies sine x and V2 multiplies cos x. Just put them in here, and we finally have our particular integral. So therefore, now an important thing to note is that we already have two constants a and b, as you can see here in the complementary function. So there cannot be any more constants. So these constants that you see here, we can assume any number for them, and we're going to set them to the easiest possible constants, which is in this case 0. So therefore, which gives us, so that gives us this yp, okay, which can just be simplified to this, because this sine x cos x and this sine x cos x, these two you can see here, and this one cancels out, and we are left with just this. Therefore, the general solution is yx is a sine x plus b cos x, okay, and that is the particular integral. So those two are basically our complementary function, and there's our particular integral, and that's the solution using the method of variation of parameters. And we'll stop here. Thank you very much.